second half of class is a second exam. I'd like to do a review session. I really don't like to wait until the night before though. And I know that you're going to be busy doing things and it's not mandatory, but I'd like to do a Google Meet review session on Sunday night. And I'm going to try and set it up so that it records. And then those of you who will really benefit from that and want to do that, then you can, and you'll still have an extra day to study before the exam. So I think the best way to do that is to create a Google invite, and you'll see the invite and it'll have a Zoom link in it, okay? I'm thinking, again, I don't want to disrupt activities during the day on a Sunday, so I'm thinking 8 o'clock at night. And again, it's not mandatory, it's just available to you if you can't Clayton.
For how long?
Probably only an hour, maybe not even that long. It's really just to answer questions. Okay?
So next Tuesday?
Next Tuesday would be the exam, right? And this Sunday would be the review session. So a couple things I want to do then today before we get into the topics, okay? And that's go through the topics that would be on exam 2 and the equations that would be on the exam, the equation sheet. So when I have this all done, Olivia, never mind. I have this all. Okay, so exam 2. Now, if you're like me, you have a personal email and you have a Kettering email, and maybe you're like me and they're both Gmail based, and you don't really know sometimes where your computer is sitting, and you go to do something and it says you don't have access. If you can make sure that you're in your Kettering system when you try and get into that meeting, you won't have any trouble. But if you're somehow into your other Gmail address, it'll say you don't have access. And you can click a button and I'll get a message, but sometimes I won't see that message. So just so that you don't have that issue when you're trying to get into the review session. Okay. So the topics start with non-steady state diffusion. And carburization. And that was the end of point defects. And then we had line defects, which were dislocations. Let me make sure, is there anything else? No. So then we had,
You can do that, but I can.
okay, I think that's it. So my equations for, that would be on the equation sheet.
issues.
I think that's it. So, our slip systems here. The slip plane is the densest, most highly packed, and the slip direction is the densest. So for BCC, the planes are the 110 planes, and the directions are the 111 directions. You won't have to come up with a list. And for FCC, it's the 111 planes and the 110 directions. And the table, let's say, will be provided. But I'm not going to identify which side is BCC and which side is FCC. Okay? Let's see, anything else? So this is and mostly calculation kind of exam. Very little in the way of concepts. The only thing I can think of as far as concepts go is this thing that I've been saying over and over again, and that is strengthening involves adding obstacles to dislocation motion. So in the case of line defects, those obstacles are dislocations, and they are obstacles to one another. Maybe we could say also Now, you don't see on there identifying primary and secondary subsystems. That's because you have to identify a primary subsystem in order to know what the critical result shear stress is. And you have to identify the secondary subsystems in order to know how to calculate the stress on the secondary subsystems. So I'm not going to ask you to write out all of the different primary and secondary subsystems. You'll just need to know what cosine phi, cosine lambda is for each of them. All right. Any questions about that? Okay. We've got our equations, got our topics, have an hour, maybe an hour and 10 minutes. I might just make the lecture a little more brief so you have more time. So you've got homework 4 returned. I haven't posted it. I can't remember if I posted it last night or yet or not, but I will tonight if I haven't. The solution for homework 4. You're going to be turning in homework 5 today. The problem with posting the solution to homework 5 is everybody's solution is different, right? So what I thought I might do before we start into this is do homework 5 all the way through with my numbers. Okay, or maybe I did that already, I started that already. I'll just pick numbers, different numbers. All right? So, while I said that we finished all the materials for the exam last time, this is an example for the exam. Okay. Let's say, my B number was 5, 2, 1, 1. So the stress is going to be 521 megapascals. And the stress direction is the 211 direction. I think I've done that one like that before. Let's make it 221. All right. And let's say, what did I say in homework? BCC or FCC?
FCC.
F? Yeah. So, I want to end up with a negative in here, just so we have an example of that. So let's make, so I'm gonna make this a negative. I think that will good. All right. So this is 1 over the square root of 3 times the square root of 5.
Did you make that 2 negative, that direction? The 2, 2, 1?
Yeah, I did that because I was afraid I wasn't gonna get any negative sign up here, but that's not, there's obviously no worry there. So wherever I have a negative value for cosine phi, cosine lambda, it means that the direction that I've chosen is causing compression, and I want tension. So I would go and just change all the positive ones to negative ones, and all the negative ones to positive ones in the direction. So here, I make that 0, 1, 1 bar, which makes this positive, which makes that positive.
Bless you. Bless you. You're welcome.
So I can see that the biggest value for cosine phi, cosine lambda is 9 over 9 root 6. So if you had to identify the primary, it's those two. And then we have 1, 3, 4, 5. So these are my secondary. And we don't really need to calculate the others. Unless I ask, well, yeah, I probably would ask for resolve shear stress. So I have 521. noting here. In other words, you didn't need to make a negative in your homework. I just did so that I would get some negative values for cosine phi, cosine lambda. So I've calculated all the resolved shear stress, right? This is the secondary, and this is the primary. So the next thing was what is the critical resolved shear stress, and it's the maximum of these. So we got a critical resolved shear stress. The only other question is, once those slip systems get blocked, how much stress is necessary on the secondary subsystems? So we have the critical resolved shear stress is 241. It's equal to whatever this new stress is times the secondary cosine phi cosine lambda, 0.23. That stress is going to be 4 times bigger. Now, a couple of things to point out. Again, Cosine phi cosine lambda should never be more than 0.5. If it is, check your math. It's a shame to have to erase this. So I'm making a spreadsheet. Didn't think about this until I was assigning it. Do you really want to have to grade every single one of these? So I'm making a spreadsheet that will be able to calculate these, hopefully. All right. Any questions about that? Any questions about homework 4? Okay, I'll post a solution. Then we're ready to move on to phase diagrams. And you have 2 different phase diagrams. One of them looks a lot like the one that we, the lithium-lexium phase diagram. This is for copper and silver. We'll start with that. The other is for steels. Iron carbon. And you'll notice for the iron carbon phase diagram that it only goes up to 6.7 in the composition. Because, well, that's the composition, 6.78% carbon is the composition of the harder phase. We're never going further than that even at all, talking about iron and steel. In fact, for most steels, we don't go any higher than about 0.8 weight percent carbon. So the part of the phase diagram that we're really working with is like that. Okay? And we won't start that until after the exam, and after the lab. Okay, so let's look at this silver, copper, silver phase diagram. You can say them in either order. Sometimes you might actually find the flipped version, and this would be weight percent copper instead of weight percent silver. Something to notice, up on top, the atomic percent. So because copper and silver don't weigh the same amount, if we wanted to know the percent copper atoms versus silver atoms, that would be this up here. Rarely do we want that. But this is why you have to indicate weight percent and not just percent when you're talking about composition. A couple other things to notice. There's a line labeled liquidus here, and then there's this is also liquidus, it's not labeled, but these lines are liquidus lines. They are the line between the all liquid phase and the beginning of solid. So between all liquid and solid plus liquid and solid plus liquid, alpha and beta. The solidus is the line between the solid and the liquid and all solid. And then a solvus line is a line between only solids. So to the left of this solvus line is alpha and beta, sorry, to the right is alpha and beta, to the left is all alpha. That's the solvus line. The point A here That would be the melting temperature of silver, 0% copper. Wait, this is 0% silver, I'm sorry. The melting temperature of copper is point A. The melting temperature of silver is point F. All right, I'm gonna draw this so I can relate this to the other things. So we've got melting temperatures of copper at here. Melting temperature of copper. Then we've got eutectic line just under 800, starting at 8. Silver, and this end is at 91.2. So this is the eutectic point, where I could have liquid, and alpha, and beta all together at the same time. This goes down to about 400. This is alpha. This goes down to this number 400. Okay, so alpha is a copper rich solution of copper and silver. It's a solution, meaning copper is dissolved in the silver, silver is dissolved in the copper. Every place I look in the alpha will have the same composition. Well, no, of the same crystal structure. And if I have a piece of alpha, anywhere I look will have the same composition. And then beta is just a silver rich. So the alpha plus beta region is a mixture of two solid phases, alpha and beta phases. All right. The eutactic transformation here sometimes it's called the eutectic reaction. It says if I have liquid with 71.9 weight percent silver in it, and I cool it through, what temperature was this? 779 degrees C. It will transform to alpha with 8 weight percent silver and beta with 91.2 weight percent silver. The two endpoints here. This product, this alpha and beta that forms from the liquid, has a very unique microstructure. So if I always use a circle because it used to be when you looked under a microscope, it was a circle. But if I have liquid, which I couldn't really see under the microscope, and I cool it, liquid with, what did we say, 71.9 weight percent silver, and I cool it, what will happen is little bits of solid alpha or solid beta will form. I don't know that it's necessarily one versus the other. Let's say that these are all little solid alpha forming in the liquid. Now alpha doesn't have very much silver in it. So as it's forming, the liquid has 71.9% silver. As the alpha is forming, it's got to kick out silver in order to make solid alpha, because solid alpha only has 8 weight percent silver. So as this forms, it's kicking this silver out, which causes the silver concentration to go up enough to make beta. And so, with time, we've got these areas of alpha, and right next to them, I'm going to make beta be black. beta's forming. Because the alpha is kicking out silver in order to form a solid. And as that happens, well, then there's a nearby area that's poor in silver, and that becomes more alpha. So there's alpha, and there's beta, and there's alpha. And so we end up getting a couple of possible structures. One would look like this. Layers of alpha and beta. Alternating. Alternating layers of alpha and beta. That's one common sort of structure. Another something like that. I mean, throughout, maybe yeah. Like that. So instead of alternating layers, one of the phases is growing in this sort of kind of Christmas tree-ish looking shape, and it's surrounded by the other phase. So white could be alpha or beta, black would be the other. So that's what forms if I have exactly that composition as I'm going. All right. So with those ground I want to make, I'll make a matrix, but I'm gonna look at so the eutectic alloy only has one composition, 71.9 weight% silver. Hypoeutectoate 8 to 71.9. Hyper 71.9 to 91.2. Zero to 8. And 91.2 to 100. This is the hypo. Hyper. And this is the off-eutectic beta and the off-eutectic alpha. So, let's say we're going to use, we'll use 20 for the hypo, we'll use 80 for the hyper, we'll use 5 and 95 for the other two. So we'll use 20. And we'll use that's 80. change that to 85, just so that nobody thinks something is adding up to 100. Coffee tactic, we'll say that's fine. And 95. Okay, all of that at, do that at 800. We'll just use the lines we have here. We'll do that at 800, at 700, and at 300.
Bless you.
Okay, that means I have to say goodbye to. Start with our packet. microstructure, 800 degrees. We're right there, right? Just above that eutectic point. So the phases that I present are just liquid. Yeah? If I look at my 20 weight percent silver, just above, what do I have? I'm in this region, so I have alpha in liquid. And if I have 5 weight percent silver, like there, so I only have alpha. 85, I have beta in liquid. And 95 of just beta. Okay? The composition of the phase, if there's just one phase, then the composition of the phase is the same as the composition of the alloy. So if I only have alpha here, then its composition is 5 weight percent silver. Alpha has 5 weight percent silver. Liquid here was 71.9 weight percent silver. And beta here with 95. If I only have one phase, then the relative amount of that phase is 100%. So here I have 100% alpha, 100% liquid, and 100% beta. It's not really possible to have a microstructure in a liquid. I mean, there's no solids to look at. So there really isn't a microstructure here. For the all alpha phase, if I could look at it that under the microscope, I would see, let's see, we said alpha is dark, right? Okay. There's no significance to the scribbly look. It's supposed to be all black. What I would see is grain boundary, which are even darker. And pay no attention to the scribble pattern. It should be solid. And I'll see even darker lines that are the grain boundaries. So this is a grain boundary. And this is all alpha. Just grains of alpha. And beta, we said beta would be white, so it makes it easier. I just have grain boundaries. Of beta. So it's all beta. That beta has 95% silver in it, and it would look like that under the microscope. Okay, what about the two-phase regions? I'm going to take this off here so I can make it 800-degree line. So I draw a line all the way across the two-phase region. And the endpoints tell me my compositions. So I'm thinking that the endpoint over here is pretty close to 8, so we'll say that's 8 at that end. And this one's sloping quite a bit, so let's see. 800, it's about 60, let's say 67. You see that on the base diagram? Okay. So for the 28% silver at 800, my alpha has about 8% silver, and my liquid has about 60, what did I say, 67? Over for my hyper, you check it. The two endpoints are, that's 91.2, we'll say that's 93, and 77. Say 93. Okay, so over here, I've got beta is 93, 8% silver. Is that right, or is that the liquid? No. liquid's at 77. All right, now calculating the relative amounts of each uses something that's called the lever rule. Call this length x. Yeah, I'm just going to call this y. Okay. The relative amount of phase one, the phase on the left, is equal to the length on the other side of the fulcrum, y, over the total length. So notice that I'm taking the length on the other side of the fulcrum. The most common error is to think that you're supposed to take the length on the same side. No, take the length on the opposite side of the fulcrum. So the relative amount of phase two is equal to x over x plus y. So in this case, relative amount of alpha equals, so here my lever goes from 8 to 67, and I'm at 20. That's alpha, that's liquid. So the relative amount of alpha is going to be 67 minus 20 over 67 minus 8. And the relative amount of liquid is going to be 20 minus 8 over 67 minus 8. So what's 47 over 59? Almost 5/6. That can't be that big. 87? One, might be closer to 80.
Yeah. 8%.
80? %, alpha, and then you could just solve for that and take 100 minus to get the relative amount of liquid. I always write the equation for both in case I make a mistake. Look, notice that I'm using percent, not weight percent here. just percent. Whereas here, I use weight percent. Also, these two don't necessarily, don't add to 100. But these two do, the relative months. All right, so let's do the equation for relative amounts on the 85 weight percent. So I'm going in 77, my fulcrum is at 85, and 93. And this is liquid, and this is beta. So the percent beta is going to be 85 minus 77 over 85, I'm sorry, 93 minus 77. And the percent liquid is going to be 93 minus 85 over 93 minus 77. 60. About 50%. Yeah. What would that look like under the microscope? Well, here, I'm going to let my liquid be white, and I've got grains of beta. I'm sorry, grains of alpha. Right. There's about 80% of it. Over here, it's a 50-50.
Should that be beta?
What's that?
Should that be beta?
Grains of beta. This should be grains of alpha. And 85. Right, we have beta here. just below the eutectic. Oh, no. Okay, so this will be, what temperature did I say? 700. All right, so again, starting with the eutectic at 700. Now I have alpha and beta. Let's see. For the 20% weight percent and the 80 weight percent, I also have, or 85, I also have alpha and beta. And while it looks like it's right on the line, let's favor me, and because I want to say that it's just beta at that's 700 for 95, and it's just alpha. I know it's like right on the line, but let's say that. Okay. So compositions of the two phases. So those endpoints, I'm going to say, are at 6 and 84. I'm sorry, 94. So for my eutectic, I've got two phases. The alpha has 6 silver, and the beta has 94 weight percent silver. When I'm down here at 5 weight percent silver, I just got alpha, and alpha has the same as the overall composition, which was 5 weight percent silver. And if I'm at 95 weight percent overall, then this beta has 95 weight percent silver. Same as the overall. There's 100% beta. And there's 100% alpha. See, sketch. Or 800 degrees C, those two. Okay. So for the other two, let's see. The eupectic line goes from 6 to 94 with a fulcrum depending on which composition we have. So the composition of these two phases is the same. When I'm at the 20, the composition of the two phases, alpha is 6 weight percent silver, beta is 94 weight percent silver. My line goes from 6 to 94 with the fulcrum at 20. For the eutectic, it goes also from 6 to 94 with a fulcrum at 71.9. And for this 85 is also the same two endpoints, 6 and 94. This time the fulcrum is at 85. All right, so my calculation, I want, this is alpha here, that's beta there. So percent alpha is 94 minus 20 divided by 94 minus 6. And the percent beta is 20 minus 6. Over 94 minus 6. So I'm setting up the same equation each time. Just the differences that have changed because the fulcrum's moved. Okay, now, here's the tricky thing. You detect it, it's just gonna, we'll use the striped sort of microstructure. So the eutectic composition is just gonna make 100% eutectic microstructure. These are just layers of alpha and beta. Okay? Just hang with me for 2 seconds. What I had over here at 700 was grains of alpha. Quite a lot, I think it was 75% alpha. I still have those grains. And it's the liquid that was left that made eutectic structure. So the original grains of alpha are still there. And wherever there was liquid, I made the striped microstructure. So I have grains of alpha from before. That's called pro-eutectic alpha, and then eutectic. And similarly, over here, we had grains of beta that were smaller. There's a little bit less of it. So these are still beta. And where there was liquid now, there's this eutectic. Typically, one of these two phases, one of these two solid phases is hard, maybe BCC, and brittle. And one of them is tough and ductile, probably FCC. And so, one of these two is not good because it's got whatever the brittle phase is in a big amount. Right? this, and then we'll start, what date's today? Tuesday, next Tuesday, we'll start with this. Okay? Was I supposed to give homework today? I can't imagine I was, with the weekend and everything good. Nah, it's on the syllabus. If I was, I'll post it. It'll be something like this.